Hello, class. This is Miss Chisholm. I'm coming to you today with the practice exam for the comprehensive final, Part B. So Part B mainly is going to cover 4 and 5. Well, I really want to say more heavily on 4, a little bit of Module 3, 3.2, because we saw 3.1 on Part A. So it'll start with 3.2, and I will work that problem or those couple of problems from 3.2, and then we'll look at some problems from 4, and then because Module 5 is the later part, I will focus on one question from 5 that you might expect to see on the final. Module 5 is not going to be as heavily present on the final. So let's get started. I'm going to share my screen. I'm going to turn my camera off. All right. So here we are, number 1. Again, this is Practice Exam Comprehensive Final Part B. So number 1 is going to be a problem that comes from Module 3. If you need to go back and review this, and it will focus on binomial, the binomial distribution. Because remember, we talked about 2 particular probability distributions, binomial in Module 3, and then normal distribution in Module 4. So here we go. Number 1, 28% of college students say they use credit cards because of the rewards program. You randomly select 10 college students and ask each to name the reason he or she uses credit cards. Find the probability that the number of college students who say they use credit cards is A, exactly 2, B, more than 2, or C, between 2 and 5 inclusive. So first thing I'm going to do is jot down my key parts here, my key pieces of information. I'm going to try not to make this video as long. It shouldn't run as long as the first one. The first one had a lot of older material that I wanted to make sure you remembered. The Part A. Part B should not be as long. Okay, so 28%. Remember, the percent is always going to be the P, but we are going to change that to a decimal, 0.28. So your probability of success is that percent that you're given. That's your P. It says you randomly select 10 college students, so N is going to be 10 here, and ask each to name the reason he or she uses credit cards. Part A, find the probability that exactly 2. Part B, more than 2. And C, between 2 and 5 inclusively. Okay. So exactly 2. And they actually show you how the probability statement would look mathematically. Exactly 2 is just a single 2. X is 2. Okay. So probability of 2 just means X equals 2. So you can use the formula, although I like to use binom PDF and binom CDF. You can use the formula here, especially since it's just a single number, if that's what you want to do. Using the formula, you would have, remember, it's NCR or NCX, P to the X, Q to the N minus X. That's the formula. So in this case, it would be 10, choose 2, 0.28 to the second, because it's P to the X. Okay, and then Q, remember Q is 1 minus P. So if P is 0.28, then Q would be 1 minus 0.28, which would be 0.72. Always just kind of double check, but 1 minus 0.28, 0.72, okay? So N choose X, P to the X, times Q to the N minus X. Or binom PDF N P X, because it's NPX. And remember, this is on your fact sheet. The formula and the shortcut key is on the fact sheet, and I will have those when you take the exam, okay? So you don't have to worry about trying to find your old one. All right, so if you use the formula, of course, 10, choose 2, you would type 10 first, then math, and you would go over to PRB till you find NCR. And now you tell the calculator what the R is, which in this case we call it X, but it's 10, choose X. And then you would place the P in parentheses, raised to the second, and then the Q in parentheses, raised to the 10 minus 2, which would be 8. Uh-oh, what did I do? Am I still in the exponent? I am. I didn't go out of that. I'm in the subtext still. Okay, now arrow up to get out of that. Then 0.28 raised to the second and 0.72 raised to the 8. There we go. 0.255, 0.255 when you round it to 3 decimals. Okay. Probability that X is more than 2 or more than 2. So probability that X is greater than 2 is what you would have there. Now this one would require, if we use the formula here, it would require us to use the formula repeatedly. Okay, so I'm not sure that you want to do that on this. We would literally have to use the formula for everything more than 2. And we wouldn't go past 10, but we would have to go up to 10. So greater than 2, we would have to use the formula for 3, for 4, for 5, for 6, for 7, for 8, for 9, and for 10. And that's why I recommend that you get comfortable with the calculator, or that you got comfortable with the calculator, because trying to use that formula repeatedly and trying to ensure that you don't make even the slightest mistake can get a little tedious, okay? And once you hit something wrong on the calculator, you got to start all the way over. Like, it would just be a lot. So I recommend using the shortcut keys. Now, with the inequality symbols, we'll use a form of binom CDF, okay? So to use binom CDF, we have to have technically a less than inequality, so we need to write that in equivalent form, and that would be 1 minus the probability that X is less than or equal to 2, because it started out greater than 2. So we say 1 minus the opposite. Less than is the opposite of greater than. There was no equality. We have equality now. And then we're able to do 1 minus binom CDF, where the N is 10, the P is 0.28, and the X is the 2 right there. And we put 1 minus in front of it because remember, we're writing it in an equivalent form. So when you type that in, make sure you type 1 minus first. So 1 minus, then press math and go over to, nope, 1 minus, then press second bars and go down to binom CDF. There we go. 10 trials, probability of success is 0.28 and X is 2, hit paste, 0.562. So again, I wrote it in the equivalent form using the fact sheet, okay? I just have them memorized, but y'all don't have to memorize them. You can use the fact sheet, okay? All right, so the part C, between 2 and 5 inclusively, probability that X is between 2 and 5 inclusive. That means including the 2 and the 5. So that would be the probability that X is 2 or 3 or 4 or 5. Okay. So what that means then is that we would have to either use the formula or use binom PDF repeatedly for 1, 2, 3, 4 of these values and then adding them up. So for the 2, we would have binom PDF, because it's exactly 2, 10.282 plus binom PDF for the 3, 10.283 plus binom PDF 10.284, and then lastly binom PDF 10.285. So when it's a single number, when it's a single value, we actually can use binom PDF for each of those individual values and then add them up. I mean, that's the only other option because this is a bounded inequality on both ends, the way this is written. So the binom CDF doesn't work with this one, the way that it's written. So to avoid the formula, the only other option is to use binom PDF and do it for each of these individually. Okay? And then getting those and then adding them all together. Okay? So that's number 1. And again, I've worked this out in old videos as well. You can go back. This is module 3. This is 3.2. If you want to go back and watch my old videos. Okay. Number 2 is getting us into normal distribution. That's a normal distribution problem. So for number 2, it says assume the random variable x is normally distributed with a mean of 83 and a deviation of 4. Find the indicated probability. So the first thing is that we're told it's normal. So I'm going to draw my curve. Putting my mean at the middle, 83. Okay. And then I'm gonna put that right here, 83. And my mean and my sigma, my deviation is 4. And then I have a probability statement, x is less than 79. Well, 79 is less than 83. So I'm gonna put it to the left somewhere. Okay. And it says less than that, so that means we will be shading all the way to the left tail. Okay. All right, so we would have normal CDF. The lower bound would be negative infinity because that's the left side lower bound. The upper bound would be the 79. The mean would be 83, and the deviation would be 4. Okay? And then putting that in the calculator, remember to get normal CDF, you press second bars, lower bound, negative 9999, upper bound 79, mean is 83, deviation is 4, and hit paste. 0.157, no, 1.159 if we're rounding it to 3. Actually, they want us to round it to 4, so 0.1587. 0.1587. Lower bound, upper, mean, deviation. A picture is always very helpful. Remember, I used normal CDF here because I was looking for the probability. When you're looking for the score, that's when you use inverse norm. Okay, remember I have videos for this as well. This was out of 4.1 if you want to go watch a more detailed video. Okay. Number 3 is also dealing with normal distribution. Similar to number 2, it just has 3 parts. So let's look at number 3, at least part of number 3, if we don't do the whole thing. It says, in a survey of a group of men, the heights in the 20 to 29 age group are normally distributed with a mean of 67.5 and a deviation of 3. And it says a study participant, which is X, is randomly selected. Part A, find the probability that the study participant has a height less than 66. So part A, probability that X is less than 66. So I'm going to draw my picture for part A. Dealing with normal distribution, bell-shaped curve, is continuous at each end, mean at the middle, 67.5. Okay. All right, we're looking for the probability that X is less than 66. Well, 66 is smaller than 67.5, so it should be to the left. 66. And we want the probability that X is less than that, so that means we're shading to the left, all the way to this left tail towards negative infinity. So normal CDF, lower bound is negative 99999, upper bound is 66, mean is 67.5, and deviation is 3. Second VARS, normal CDF, negative 99999. The upper bound is 66. The mean is 67.5. The deviation is 3.3085. Okay. Part B, I'm going to show you that one. B says find the probability that a study participant has a height that is between 66 and 71. So probability that X is between 66 and 71. So with this one, I'll scoot it up some. I'm going to draw my picture again. The mean is still there at the middle. 66 is a little smaller than 67. So I'm going to put 66 about here. And then 71 is a little bigger than 67. So I'm going to put it over here. And we want the probability that X is between them. So we're looking for this shaded region between those two bounds. That shaded region there. So normal CDF, the lower bound is the left side bound, which is the 66. The upper bound is the 71. The mean is 67.5 and the deviation is 3. Okay. And then there's a part C as well. And part C says find the probability that a study participant has a height that is more than 71. So part C, let me see if I can zoom out here a bit. So you can see all three parts. Part C is probability that X has a height that is more than 71. So whereas this one was less than on part A, this one is more than, which is greater than mathematically. Okay, so if you had your picture for this one as well, your mean at the middle, 71 is bigger than 65 or bigger than 67. And then you want the probability that X is greater than that. So that means you're shading the right tail this time towards positive infinity. So this would be normal CDF. The lower bound is 71. The upper bound is 99999. Then you got 67.5. And then you've got 3.0. So lower bound, upper bound, mean mu, deviation. And the answers are at the back of this. I remember I gave you a copy of this in class so that you could follow along with me on it. But the answer For Part B, we already got the answer for Part A. The answer for Part B was 0.5698, and for Part C, 0.1217. And because all of your probabilities are greater than 0.05, none of these events are considered unusual. All of your probabilities are larger than 0.05. Okay? They're all greater than 5%. So none are considered unusual. I think because number 3, they ask you. Okay? Let's see what else we've got here that I want to look at. All right, so I do want to work number 4. I'll do number 4 and then number 6, maybe. Yeah. Okay, so let's take a look at number 4 here. It says the weights of bags of baby carrots are normally distributed with a mean of 28 ounces and a deviation of 0.39. Bags in the upper 4.5% are too heavy and must be repackaged. What is the most a bag of baby carrots can weigh and not need to be repackaged? Okay, so to not need to be repackaged means that it has to not be within this area. It has to be, this is your area in the upper right-hand quadrant of your, not quadrant, the upper right-hand tail of your curve. So if you had your mean there at the middle, 28, and we're looking for the most that the baby bag of carrots can weigh, so we're looking for the most X that would not place the bag in the upper 4.5%. So upper 4.5% would be this area in the right tail, 0.045. So we want to know what is the minimum X, the minimum, or the most rather, what is the maximum X that the bag can weigh without getting into that area. So what we're going to be doing, since we've got the area, we're going to be using inverse norm to get the score. Okay? An inverse norm requires that we use the area to the left. Right now, we got the area to the right. So to get the area to the left, say 1 minus 0.045, because the total area is 1. So 0.955 is the area to the left. And then our mean is 28. And our deviation was 0.39. So the most that the bag can weigh without needing to be repackaged, 0.955, 28, and 0.39 is 28.66. And they want us to round that to 2 decimals, so 28.66 ounces. Okay, this is number 4. Again, on practice exam part B for the final. Okay. All right. Let's look at number 6. And then there's one question out of module 5 that I do want to look at too. So let's look at number 6 here. It says the weights of ice cream cartons are normally distributed with a mean of 7 ounces and a deviation of 0.5. It says on part A, what is the probability that a randomly selected carton has a weight greater than 7.1? So on part A, we're talking about a single carton X has a weight greater than 7.11. So we're looking at the probability that we could select a single carton and it have a weight greater than 7.11. So our mean is 7. 7.11 is a little bit bigger than the mean, so I'm going to put it over here to the right. I want the probability that X is greater than that, so we're shading all the way to the right tail towards positive infinity. So with part A, this would be normal CDF. Our lower bound would be 7.11. Our upper bound would be 99999 because of the right tail. Our mean is 7, and our deviation is 0.5. Lower bound, upper bound, mean, deviation. Okay? So part A, second bars, normal CDF. Lower bound, 7.11, upper bound, 99999, mean is 7, deviation is 0.5. Hit paste. We get 0.41294, and looks like they want us to run it to 4 decimals, so just 0.4129. Okay. Now look at part B. Let me stop sharing for a minute. Looks like I froze up. Okay. Okay, I'm back sharing now. Sorry about that. My camera froze up. All right, look at part B now. It says on part B, a sample of 36 cartons, so N is 36 here, is selected. What is the probability that their mean weight, so that means the mean weight of the sample, is greater than 7.11. So probability that X bar is greater than 7.11 is what we're looking for here. So for part B, this is a sampling distribution. So because our sample is big enough, and also because they told us at the beginning that our original population was normal, then our sampling distribution is also normal. And that means mu sub X for our sample distribution is equal to the original mean mu, which is 7. And sigma sub X is equal to our original sigma divided by the square root of our sample size. And so that would be 0.5 divided by the square root of 36. So that would be 0.5 divided by the square root of 36. So that would be 0.08333. Okay. So we had to reduce that deviation, and I always try to go at least 4 decimal places there because the final answer has to be rounded to 4. So now we're ready to draw a picture. Okay. So this is for our sampling distribution. So our mu sub X is equal to our same mean mu. And then we're looking for the probability that X bar is greater than 7.11. Well, the deviation is a lot smaller now. So that 7.11 is like 2 deviations from the mean, or almost. So I'm going to put it well over here, 7.11. And greater than be this area here in the right tail towards positive infinity. So it should be smaller. It should definitely be a smaller probability value. Normal CDF, 7.11 is still our lower bound. Okay. Our upper bound is still infinity, 99999. Our mean is still 7, mean mu sub X, but our deviation is now reduced 0.08333, whereas before it was 0.05. Remember, when you're dealing with the sample, your deviation gets reduced. Okay? So we put that in, we press second bars to pull up normal CDF. The lower bound is 7.11, the upper bound is 999, the mean is still 7. The deviation is now 0.08333. Hit paste. 0.0934. 0.0934. And that again was number 6. It had a part A and a part B. Part A was just pulling a single X from the population, whereas part B was a sample was pulled, and we were interested in the probability of their sample mean being greater than 7.11. Okay. I'm going to work this one, number 12, and then I am done for today. This one is dealing with Module 5, hypothesis testing. I just want to, since that's a newer topic, one of the later topics, I just want to do one more of these. A random sample of 82 eighth grade students' scores. So we're talking about the sample scores. Sample of 82, so I'm going to put 82 here. Had a mean score of 263. So we're talking about the mean from that sample. So that's X bar. This 263, that's X bar. Then it goes on to say this test result prompts a state school administrator to declare. So here's the claim. To declare that the mean score for the state's eighth graders on this exam is more than 260. So this is his claim about the whole population mean, the whole population of all the eighth graders. So the claim, this score, this test score from that sample prompted that administrator to claim that the mean score for all the eighth graders is more than 260. Okay, that's the claim. It says, assume the population standard deviation is 37. At alpha equals 0.07, is there enough evidence to support the administrator's claim? All right, so there is our claim. So the first thing that we do is set up our hypotheses. Now, your claim is a strict inequality. So because it is a strict inequality, meaning it does not contain equality at all, it has to be HA then. So HA is our claim. Now that we have HA, we should be able to get HO. We should be able to get the null, H naught. Still the mean mu, still 260. The opposite of greater than is less than. And then also keep in mind that the null must contain equality. So less than or equal to. Okay. Now, let's draw a picture that illustrates what kind of test this is. HA tells us that this is a right-tailed test. The symbol on the alternative hypothesis, the symbol used, tells us what kind of test we have. This is a right-tailed test. Okay. So here's our mean. Actually, I don't even have to do that. I don't know what I'm thinking. Right-tailed test. Here's this area. Okay. Now, it wants us to find the test statistic, the p-value, and then make a decision. To make that decision, we compare p-value to alpha, which I'll write on here, and then interpret our decision. So I'm going to let the calculator get the test statistic and get the p-value for me by performing a z-test. Okay? Z-test to get test statistic and the p-value, which is just the area in this shaded region. So we're going to use the z-test. And how do we get a z-test, or how do we pull up the z-test? You press stat and you go over the test. and it's the first one. That's the one we're using. Okay, now you have options here. Do you want to enter in the data, which means you have all the data entries and you have to put them into a list? Or do you want to enter in the stats, which is what we have, the sample size and the sample mean? We have the stats. We don't have the actual data set. We have the stats already calculated for us. So we're going to make sure that we choose stats, and it's highlighted, and then we're going to enter in our values. That mean value is our claim value, 260. Our deviation is given, our population standard deviation, sigma, is 37. Our sample mean, X bar, is 263. And our sample size is 82. And then right here, you're going to choose the correct test that you have. Don't worry about the fact that they've got the little mu sub naught, the mu sub 0. That's just saying what kind of test, how are we testing the mean claim, okay? How are we testing the claim value? But what you do is you just choose the matching symbol that's on HA. So you have to use a right tail test, so we have to make sure we choose the third one, the greater than symbol. It should be the same symbol that's on HA. So we choose that one, and then we go down here to calculate. So our Z score, our Z test statistic is 0.73, and our p-value is 0.2314. So Z rounded to 2 decimals is 0.73. Our p-value rounded to 3 decimals is 0.231. And then we will compare, to make our decision, we compare p-value to alpha. Alpha is the test level, the level at which you're testing, which we're told that we're testing at 0.07. So when we compare p-value, which was 0.231, to alpha, which is 0.07, p-value is definitely greater. So we fail to reject H naught. When p-value is bigger, we fail to reject. Okay? And because we failed to reject H naught, that means we still have H naught and we still have the claim, HA. So honestly, that means we don't know which one is the answer. So because we weren't able to throw out H naught, that means we didn't have enough evidence to support the claim. Had we been able to throw out H naught, then all that would have been left was HA, and therefore we would have supported the claim. But we did not have enough information to throw out the H naught. So we say at the 7% significance level, there is not, because we failed to reject. Anytime you fail to reject, you say there is not. There is not enough evidence to support. There wasn't enough evidence to support the claim because the claim was HA. Okay? Okay. Please go back and watch any of my old videos if you need more assistance on these, where I go into more detail on the specific topic for each section. Okay? And if you can work through these reviews, you'll be just fine on the test. So final exam coming up. Study hard. Bye-bye.